Okay, good morning. Thanks for coming. I'm going to talk very briefly about what's been happening within my research group with R matrix calculations. Those of you who are familiar with Quantemol N will realize that this is a program to run the R matrix codes, and what I'm going to talk about is what's happening outside Quantemol N, in other words, developments that haven't yet made it into that software. This is the Duffer's Guide to R matrix theory, which basically says you divide the world into two regions, and if you want to do an electron collision from some target molecule, you put your target molecule inside a spherical box big enough to hold the target molecule wave function, and you solve a complicated problem in the inner region and a simple problem in the outer region and put the two together to get your answer. And the advantage of that is that you can solve the complicated problem in the inner region once, because it doesn't depend on the energy of the scattering electron. And in the outer region, when you come to doing the simple problem, you solve it on a very fine energy grid, so you can get all your cross-section features or your detailed rates or whatever it is. In slightly more detail, in the inner region, you basically have a quantum chemistry problem based on proper treatment of things like the exchange between the electrons and the electron-electron correlation. In the outer region, you simply say the electron feels, say, the charge on the molecule or the dipole on the molecule, or whatever the long-range couplings is. And then you have a boundary in the middle where you have to assume that the target molecule has no effect, it's dead. So the wave function is zero, and that defines the boundary. That's a very brief introduction. If you want to know more, this article will tell you more than you possibly want to know. It's basically as a comprehensive review, which I came out about 8 months ago on electron-molecule collisions with the R matrix method. So we've had a number of recent developments which using the codes. I put down positron-molecule collisions as recent developments. In fact, when I first came to UCL, which was more than 25 years ago, I put positrons into the R matrix code, but they sort of fell out again. And about 3 years ago, we reinstated the positron molecule collision project and have indeed added positrons being the antiparticle electrons, they annihilate, and we've added actually the ability to calculate positron annihilation, which was something we didn't do before for the rather pragmatic reason that we knew the answer was going to be awful, so we didn't want to calculate something which we knew was going to be terrible. I have to say, because of the methodological developments we made in the meantime, and in particular the last topic here, the use of pseudostates, actually the answers really are now very good. The second thing is a slightly technical development. It's called the partitioned R matrix method. It allows you to do much bigger calculations than the ones that are routinely done. When you solve the inner region problem with the R matrix, in traditional R matrix theory, you need all the solutions, and that actually puts a limit on the size of the problem because it involves a matrix diagonalization. You can normally, on a standard computer, diagonalize something of a few thousand, maybe 10,000 if you've got enough memory. With the partitioned R matrix method, my student working on positron physics successfully diagonalized a 600,000 dimensional matrix, because we now have a method whereby we only need to use the lowest few solutions and we correct perturbatively for the other ones. We have in order to do these very large calculations, we've moved to a 64-bit implementation. That is slightly less trivial than just changing the compiler options. You did actually require some reprogramming, but I'm not going to dwell on that. The only thing I'm going to talk about in any detail is the R matrix with pseudostates method, which I think is actually very much where the future is going for actually improving the quality of these calculations. So pseudostates are a method of basically giving you a second continuum. You have a first continuum because you have your electron coming in over the target molecule, and pseudostates allow you to actually represent the continuum of the target. So when the target itself is ionized, for example, that produces another continuum. So originally we started looking at them for impact ionization, and I'll discuss that briefly, and I'll also say, well, actually, I don't think why that is the future. But if you can actually get the impact ionization right, what it allows you to extend the range of the calculation. So standard R matrix type calculations are normally only any good at low energy being defined as the ionization, below the ionization energy of the target. With this method, you can actually go into above that threshold region, which is quite important for a lot of applications. The real thing which makes this method I think particularly powerful is actually it gives you a very good representation of the target polarization. And all scattering methods struggle with that, really getting the detailed physics right. And for positron physics in particular, they allow the electron-positron correlation and annihilation to be treated correctly. And the two are related. That's really a polarization effect. So I'm not going to spend very long on this slide, but this is actually the formal inner region wave function one uses for, we don't have a stick here. No, okay. For R matrix theory, the first summation there is simply a target wave function times the continuum one, and the second one corrects all the other bits. I'm not going to talk about that at all. Normally you use a number of physical target states, for instance, if you're doing electronic excitation. If you want to then do ionization, you clearly get an infinite number of target states potentially below the ionization threshold, and you try and do a sum like that, you have a real problem. Now, that's where, as I said, we started using the pseudostates method to actually allow for that expansion. I should point out before I do that that in the literature are a bunch of semi-rigorous or semi-empirical methods for doing impact ionization, in particular the Bev method, which is implemented in Quantemol N, and unfortunately they're disgustingly good. So we labour for a long time to do this completely ab initio, but actually you can get a very simple calculation which gives you essentially the same results. To do the pseudostates, you use the same equation, but you actually change the definition of this phi n, this target wave function. So now instead of just representing the actual physical states of the targets, you add on a whole lot of extra states which represent the continuum in some discretized term. They're not a continuous set of functions, they're not an infinite set of functions. They're a discretized version which you get by diagonalizing the target Hamiltonian. They don't represent real physical states, they represent states in the region of the R matrix box. And hence they're called pseudostates. And it's probably easier to see what we're talking about here pictorially. So reality is this is actually C2 minus, which has a finite number of target states, and then you have a continuum above it. The pseudostate representation of this is the same finite target states and then a discretized continuum, looking like that. And that's clearly a cartoon. These are real numbers taken from a calculation on lithium-2, showing in our standard R matrix calculation what states we got, and then with the pseudostates how you actually get this as a discretized thing. And the lithium-2 gives almost perfect results. And this is actually the molecule with the highest polarizability of any small diatomic, and it reproduces that pretty much exactly. So that's a way of representing the lithium in the region of the lithium-2 in the region of the R matrix box. We started off with a calculation of H3+. We actually chose H3+ because we thought it was well known, because there was a previous R matrix calculation by me and one of my postdocs, and a cone variational principle calculation by a group from California. And they got the same answer, so we were naive enough to think that if two theorists agreed with each other, that was actually the right answer. I'll show you in a minute it turned out not to be. So we did electron impact ionization of H3+, and the black line is our result. This line here is actually the Vanier law prediction for the same thing, and you can see below about 1 eV. We agree with that sort of theoretical model of what goes on. There's no actually experimental evidence on this molecule, but we did a similar calculation on H2 where we reproduced the experiment. But as I say, the Bev calculation gave you the same H2 experimental cross-section in about 5 milliseconds. So this is probably not the method one would want to use for doing electron impact ionization. But when we start looking at resonance positions below the thresholds, this is electronic excitation of H3+, what you can see is that compared to the 6-state calculations, which was the old previous studies, everything has moved down. And the 6-state studies were both R matrix and the one due to ionoral using the cone variational method. When we looked at it and we started saying, how are we representing the target polarization, it turned out that the previous studies, the 6-state study, had basically missed all the perpendicular polarization. So the perpendicular polarization, H3+ is flat, is the polarizability of the molecule in this direction. And with the pseudostates, we're actually capturing this virtually perfectly. And this was actually really quite an important message, so that I had a MSc student come and actually study a lot of molecules looking at this. And what you find is that with the RMPS method, you can basically converge the polarizability in, well, he's using about 30, 40 states here. But with the standard method, it never actually converges. So just to give one example of using it, there's a long-running problem that the experiments in the Astrid storage ring in Aarhus had looked at electron impact attachment on C2-, and rather surprisingly found that the electron was trapped by the C2-. This is counterintuitive because if you have an anion, you shouldn't expect it to trap another electron, particularly if it's very small like C2. So the real question is what was happening here? Why were the electrons being trapped? And these resonances actually appeared above the photodetachment, the electron detachment threshold. So they were in the continuum. So you had to have a method which would actually be capable of treating this continuum. So to study this problem, we needed collisions from an anion, which we've never actually done in the code before. We needed the R matrix with the pseudo-state method. And because the calculation is very big, we needed the partition R matrix method as well. Well, the first thing we did was do some anion runs. An electron collision eigenphase of a pure anion with no other potentials should be 0. And rather to our surprise and gratification, that's what we got. So at least the code worked correctly for doing anion collisions. Then we started looking at using RMPS calculations and indeed getting some resonance features. That was one resonance at just below 5 EUV was known previously. But when we do the RMPS calculations, what you can see is doing a number of calculations. You get all these pseudo features, which I'm not going to talk about here, but I'm happy to discuss with people. But you get one big resonance feature, which is reproduced in all the calculations here. And it turns out that's for one symmetry. It turns out there are 3 resonances in the system, the low-lying one, which had been known previously from quantum chemistry work by Sommerfeld, and then 2 high-lying resonances. And these reproduce the experiment quite nicely, but completely disagree with the interpretation of the experimentalists in what they were seeing. So you can see there that we have resonance features here, which are roughly in the right position as the experiment, but you might notice that our cross-section doesn't appear to agree terribly well with the experimental cross-section. This turned out because we were just looking at the low partial waves, L up to G equals 4, and if you have Coulomb collisions, this is a very, very long-range effect. You have to consider all the high partial waves. So we put those in using the Born method for actually doing the collisions to high energy, and you can see we actually ended up with something. It's not perfect agreement with the experiment, but it's pretty damn good considering there was no previous explanation for what was going on here. And before you start wondering why we're not working here, the experiment must be 0 below here because this is the threshold for the process. So you get some idea the experiment's actually pretty noisy. So you have to be a bit careful about what you're looking at. So the conclusions are that the RMPS method, or the molecular implementation for it, the MRMPS method, extends the range of calculations, can treat near threshold ionization, improves greatly your representation of polarization, and we've done this now for a number of systems. For instance, it gives excellent results for positron molecule collisions. This particular treatment, though, you require high L functions. We've gone up as far as, how's it go, KLH. We've gone up to K functions. We'd like to use I functions, but currently can't do the integrals. So you have to go up to these very high angular momentum functions. So, as I said, those are the sort of recent developments. What are we doing? What is on the horizon? We have an OpenMP implementation for the codes. That means that if you have a desktop computer with, say, 8 processors on it, if you use that compilation, the computer will use all 8 processors instead of just running in one of them. That can be extremely beneficial for some of the diagonalizations. We're working on an MPI implementation, MPI being where these things are now connected with some sort of InfiniNet type communication system, and you have a lot of different boxes. That's in progress, and it's clear that to go to the next stage in size of calculations, we need an MPI implementation. We've got bits of that working, but we don't have a complete code. And as part of that project, we're actually looking at a time-dependent implementation so that we can actually begin to look at molecules in very intense laser fields. And the laser fields then oscillate very rapidly with time, so you need to actually consider time-dependent processes. We have a formalism for doing that. We have an implementation of that formalism in the inner region. We plan to use the atomic people's outer region. At the moment, we're working on matching the two together, actually taking what we've calculated in the inner region and matching it with the atomic physics outer region. Okay, I think Anna told me I had to finish at 11:20. That's about right, so thank you very much.